can start, sir.
Good evening to everyone. It's a very happy occasion that we celebrate World Space Week every year. And this one of the talk is on space transportation system, present and future. We'll just consolidate what ISRO has achieved so far and what are our immediate future plans, and then how do we plan to go about. I'm Sivakumar. I'm presently the Program Director, Space Transportation System, as well as holding the Project Director's post of Next Generation Launch Vehicle. And I'm placed at Vikram Sarabhai Space Center, Thiruvananthapuram. And you can see a host of vehicles that have been operationalized, and then they are under development, and we are conceiving for the future in the very opening slide. We'll go into the details in subsequent slides. What is a space transportation system as a requirement? That is to safely take a payload, which can be a crew or a cargo, to an intended designated point on the orbit, or from the orbit back to Earth. This everyone knows. Then, when you now look at it, the orbit has various definitions. We have a LEO, which means the low Earth orbit, and geostationary orbit, we call it as a GSO, or the planetary positions like the Lunar, the Moon, or Mars, or any other outer planets. So, going from one point to another point in orbit requires a different class of transportation and the power systems and associated protective systems that require. Similarly, going from Earth to orbit requires a kind of a vehicle configuration as well as the power and energy management. Coming back from the orbit also requires a different level of structural design, the vehicle configuration, and the energy management, because we are coming with a very high energy level which need to be killed. Whereas from going from ground to Earth, from Earth to orbit, we need to add a lot of energy into the system to reach that particular orbit and be there. But when you travel to the outer space, we need to go for a very long distances, and we need to have an appropriate propulsion system we may not be able to do with the conventional propulsion systems here. So a host of requirements are projected in the slides, and the intention of a space transportation system is to have an assured access to space in a cost-effective, reliable, and efficient delivery of payload. As I told, the payload can be cargo or human or any other scientific experiments. And it is of two types. It can be either exploratory in nature, that when you go to the lunar surface or Mars or outer planets, it becomes an exploratory. And the utilization point of it, when you go to the LEO, and then we use communication satellite, resource mapping satellites, all weather forecasting, what type of applications you develop, you put a satellite in place, and then we utilize the capacity of the vantage point of being in orbit to reach the entire Earth. Coming to this particular slide shows the evolution of the launch vehicle ISRO has ever built, and this shows the maturity that we have attained today, starting from a very humble beginning in 1963 with the sounding rockets, going into the 1980s with a 40 kg LEO payload using the SLV3, subsequently to the augmented satellite launch vehicle. These were the learning platforms for all of us. Using the technology that we have learned using these vehicles, we have built the PSLV, which you are aware is our workhorse vehicle. And from there, we have upgraded to a geostationary launch vehicle with a higher payload with a complex propulsion system we'll address in the subsequent slide. And we all know about the LVM3 rocket, which is the biggest rocket ISRO has in place. Recently, we have developed another launch vehicle called Small Satellite Launch Vehicle, which is meant for launching small satellites into a low Earth orbit. In addition to that, ISRO has managed very complex missions. When you look at it, the Chandrayaan, we did it in 2008 to going to the Chandrayaan orbit, that is a lunar orbit, getting inserted. Then subsequently, Chandrayaan 2 and 3, we have did the landing in the Chandrayaan 3 successful landing, and of course Chandrayaan 2 was did not go well. But then with Chandrayaan 3, we have exercised or mastered the technology of soft landing on the surface of the moon. Coming to the Mangalyaan also, you all know in the very first attempt, we were able to reach the Mangalyaan orbit, and we were able to demonstrate our understanding of the total mechanism of reaching that point, which is called the mission planning and execution. Similarly, we have built a very complex spacecraft, AstroSat, and Aditya L1, which is also recently in the limelight, which is almost like 15 lakh kilometers from Earth, and then positioned at the L1 point between the Earth and Sun, and observing continuously the Sun. Coming to the recent technology development on the vehicle side, we had a test vehicle, which is essentially meant to demonstrate the performance of crew escape system, which is an essential part of a manned missions to the orbit. So that is the technology we have recently developed and demonstrated. And the reusable launch vehicle, the landing experiment and the hypersonic landing experiments both have been completed, and we will be planning to work. We'll go slightly look into the details now. Go to the next slide. Okay, this PSLV, as you all know, it is a very, very versatile vehicle. There were almost like 63 plus missions we have had, launches we had, and we have sent payloads to various orbits. You can see the GTO or the inclined orbits or SSTO or all type of orbits, multiple orbits we have now sent. It has carried 104 satellites in the PSLV C-37. And today, out of 420 plus satellites what we have launched, almost 98 or 99% of the satellites are launched using PSLV. Very few launches are made using other launch vehicles. So that is the kind of versatility we had, and some of the most important missions that we have done using this vehicle is listed at the below. And all the Bhuvan portal, our weather forecasting, everything is managed, or the satellites that have injected using PSLV helps in doing the self-reliance in this area. Going to the GSLV is a next step forward in the present capability. We all know about its capability, and the first stage, that is the first indigenous cryogenic stage development, is the milestone of this particular vehicle, and it is one of the complex technologies that we have ever developed, and we have successfully demonstrated. And we have two variants of the payload. One is an grade payload, and another is a 3.4 meter metallic payload. And the very next flight we will be having a very interesting payload. We call it as an ISRO, one of the very costliest spacecrafts ever built, and it will be flying sometime in January. Going to the Mark 3, this doesn't require much of introduction. This is the present, the hallmark of ISRO. It's one of the highest capable vehicle, 4.3 ton to the GTO, and then 10 ton to the DO payload, with a lift-off mass of 640 tons. It has a very simple vehicle architecture. Of course, it employs all the three types of propulsion, both solid, liquid, as well as the cryogenic liquid. And the commercialization, the very first operational flight itself, it has carried the Chandrayaan 2, and then M2 and M3 were the commercial missions, and Chandrayaan 3 was launched in the M4 vehicle, and Chandrayaan 4 also will be launched using this vehicle. Now, the important highlight is here is again another indigenous cryogenic engine of high thrust engine, that is called a 20 tons of engine thrust we have developed, which is the major workhorse or the major energy supplier to the vehicle and payload improvement. And we are further modifying it to be a human-rated vehicle with appropriate improvements in margins and systems and reliabilities, as well as on the software, as well as the health management, monitoring, and crew safety systems. All are implemented, and the vehicle is now ready. Coming to the new vehicle, I talked about the SSLV, which is a 2-meter class vehicle, 34-meter long. It can take almost 500 kg payload to almost 500 kilometer orbit. And we had successful development program completed recently with the launch of D1, D2, and D3. And 16th August, we had it, and then it can be produced. The real advantage of this vehicle is a on-demand launch. That is, within 3 days, you'll be able to build the total vehicle and launch it. And it is of very low in cost as compared to any of the vehicles we have developed. And minimum launch pad occupancy. So we can, at a very fast rate, we can launch. That is, consecutive launches you want to make it, as well as very fast rate, immediately you want to launch, that can be managed. The test vehicle also I have talked about. This was again successfully demonstrated on the 21st of October 23. And here you can look at it, all three modules. It has 3 different modules. The vehicle is a new vehicle. The crew escape system is also a new system that need to be demonstrated for the Gaganyaan program. And of course, the crew module also has a series of satellite parachutes and systems which need to be ejected at appropriate time. And this crew module aerodynamics also plays a very important role. So the crew escape system along with the crew module, all 3 systems have been successfully demonstrated, and we were able to get the data as predicted in flight. Reusable launch vehicle, when it comes, we have had 2 flights. The first one was on May 23, 2016, which is almost, the vehicle has gone to almost like a Mach number of 5 and then landed on an hypothetical runway on the sea. Whereas in the subsequent next missions, that is the landing experiment missions, we have taken the vehicle to an appropriate altitude and by an helicopter and detached, and the vehicle automatically aligned and then landed to the land strip or the airstrip with a very high accuracy. You can see on the right side top corner on the center line with the runway center with less than few centimeters of accuracy. It came on an autonomous landing. It landed, and twice we have already demonstrated with a different maneuvering. So this shows what confidence the winged body reusable launch vehicle experiments, the technology demonstrated. The technologies demonstrated include the aerodynamic validation, precise navigation system, approach and landing maneuver, all were demonstrated using these experiments. Coming to the space vision, the way ahead, recently Honorable Prime Minister has declared the space vision, which talks about we need to send an Bharatiya Antariksha Station module, first module by 2028. We need to have an operational Bharatiya Antariksha Station by 2035, and then we need to have a lunar flyby before we go into an actual manned mission to the moon on 2040. So this is an enormous task, in fact, because all are completely new to us. That is our space habitat or the space module buildup, as well as the lunar landing requires a different dimensioning of the vehicle, as well as the systems that into that. And we can see the projects planned. ISRO has announced various programs, including the Venus missions, the Martian exploration. All these are under the study, and many of these things are already approved by the government. And this leads to a significant thrust in the R&D and exploration missions. When you go now, that next step, we have achieved up to 5, or the present LVM3, we have a capability of 4.2 tons. And with the already approved programs, we'll be able to increase their payload to 5.2 tons to GTO. But those payloads are inadequate to talk about this kind of missions. So when we now talk about a new vehicle, when we try to configure, the various factors that need to be considered are listed here. What are all the technology trends? What are all the emerging challenges? The existing technology modules, the strategy by other nations, the spacefaring nations they follow, the global trends, and the national and commercial requirements and demands. All these things have to be considered together while we configure a new vehicle. When you look into the last decade or so, the major changes we could see, the 4 major changes what we can list here is the entry of private players. Because the volume of activities are large and there are multitude of people started working in this, and now world over this is the scenario. There are very capable, extremely brilliant teams are working on various vehicle development in the private sector. Coming to the reuse and recovery technologies, today the cost of launch vehicle has been brought down by the reuse of major cost component in picture. It gives you 2 advantages. One is a production rate can be controlled, because when you are trying to reuse, we are recovering and then refurbish and reuse, the industry load will be coming down for a period of time, and the cost also is very less. The third major change that goes into are the constellation satellites that come into. That is, it talks about that instead of a very heavy GTO payloads, the world is moving towards more and more constellation of small satellites placed at an appropriate altitude to give an equivalent either the connectivity or bandwidth or whatever you call it. So these, all the 4 or 5 parameters listed at the middle, that is a private sector involvement, reusable launch vehicles, miniaturization, and small satellites, satellite constellations, technology advancements, and new propulsion systems. Again, new propulsion system, when we talk about in the last decade only, we got into large methane. We'll be talking about it slightly later. And this is the global trend. We can see the price has come down today from a very high value to maybe 1 order less today. So any new vehicle, when we conceive, we should be competitive enough in terms of the cost, and we should be able to offer back to them on a commercial basis. Only then a program will be sustaining. So from a high performance optimum systems to a low cost, reliable, and environmental friendly is the design shift or the design paradigm today. and everybody talks only in terms of the cost and the reliability, how successful you are and how lower cost you will do that. And for that, the major technology enablers will be addressing it. And when we come to the need for NGLV, we talked about the national program. In present launch vehicles, what we have, PSLV, GSLV, and LVM3 will not be able to meet the kind of module requirements, because we are targeting something like 20 tons to the LEO from the present Mark 3 capability of 9.2 tons. And the GTO capability, presently we have 4.2 tons from Mark 3. With an augmentation, we'll be able to touch almost 5.2. And from there, we are talking about 9 tons. And with an appropriate strap-on, if I can further increase it to 30 ton to LEO and almost like 12 ton to GTO, with a near similar cost or with a 1.5 factors of the cost. And the payload fairings we talk about is very large in nature, which will accommodate the very huge space stations that are called for, or special observatory payloads or anything, or the constellation of satellites can be placed there. And these kind of requirements will come when we go for a flyby missions. This kind of a payload mass are required if you want to make a meaningful sample return mass to come back. We need higher payload into the orbit. So these are the basic drivers and the targets we have taken into. Coming to the NGLV, this project is already announced already sanctioned by the Government of India, and we are into the detailed design phase. It is a 3-stage vehicle, and it is made in a modular architecture. And the new technology here is the reusable first stage and the LOX methane engines, which is a new propulsion system, which is the order of the day. Only hardly 3 or 4 engines are flying in the world. VTVL technologies, advanced avionics and navigation, because we'll be going for a totally different architecture, because all PSLV, GSLVs we conceived about 20 years back. The total architecture is now revised and then very optimized and miniaturized. But then when it comes to the manufacturing sector, it is going to be very challenging. We are talking about a very large tanks of size, 20 meters, 40 meters of stage, 90 meters of the vehicle getting lifted, transported horizontally, vertically lifted. And those challenges are enormous in front of us. And of course, when it comes and lands, there are 2 potential possibilities. One is to return to launch site. Therefore, we need to have a launch site where it can be safely recovered. But in order to increase the payload, we need to recover the spin stage downrange on the sea. So we need to develop an appropriate barge, and then the transportation from the barge to the jetty, unload, refurbish, and again take it back to the launch pad. It requires another domain. These are all absolutely new to ISRO. And these are all the focus area. The manufacturing is going to be the key area. We need to go for a very large, high volume production rates of manufacturing. And the low cost, we talked about how to bring down the low cost. So this what we talked about. The enabling technologies would be reusability and the advanced propulsion system. Because essentially, it is the propulsion system that talks about the efficiency of the vehicle. And therefore, we need to have more and more advanced propulsion system. And as far as the reusability is concerned, it can be a partially reusable or a fully reusable. Today, already vehicle configurations are declared by other nations in a fully reusable mode. And these are some of the vehicles which are already configured and flying abroad in the other nations. As far as the vertical landing or a horizontal landing, 2 options are available. But always the upper stage has to have a horizontal landing or a wing body supported vertical landing. Otherwise, your structural mass will be enormous, as seen in the Space Shuttle program. Space Shuttle was one of the very first vehicle which is used near, we can say that other than the central core, almost all the strap-ons and the vehicle. Space Shuttle itself was brought back successfully way back in 1980s. And that concept used very large amount of energy to reduce it and then recover and refurbish. And therefore, in the recent technologies, as done by the others, have a vertical which is requiring a propulsive assisted landing. Coming to the advanced propulsion system, we talk about the air breathing propulsion, because in any launch vehicle, the oxidizer is one of the heaviest element. And if you are able to manage all the oxidizer from the air available as within the aerodynamic regime of flight, it will give a very good saving on the lift of mass. And long duration deep space propulsion, we need to have a different approach. The conventional systems do not work. And of course, the high thrust propulsion system also is very important. When we talk about bigger and bigger vehicles, of lift-off mass very high, we need to have a high thrust propulsion system also. Coming to the recovery, there are various options, but when we talk about a high mass stage to be recovered, we need to go only by the propulsive system. The other systems are okay for up to a certain level of mass, and then the velocities we talk about. When we talk about a very controlled descent and then very accurate about of landing, we need to go with the propulsive based system. In vertical takeoff and vertical landing, again, it is a new area we will be venturing into, which requires a throttleable and a restartable engines. And of course, in very advanced navigation systems, we need to have inertial system, we need to have a deployable landing leg and appropriate energy dispersion or energy absorption system we need to have, and steerable grid fins we need to have the control during the non-propulsive phase. When you look at it, these will be demonstrated in two phases. A separate smaller scale vehicle will be developed, and all the learnings learned through that will be directly applied to the booster stage in order to have an economical advantage of development. And once in the full booster stage also, the number of tests will be limited before we take off into the actual flight. But then what happens to this vehicle as we develop? And this vehicle can be economically used so that all the development money can be appropriately accounted, and this can be converted into a tourist vehicle. And by the knowledge we have gained through the crew module program of Gaganyaan, we can go for an Indian space tourism project also. Is readily available in the study. And internationally, it is going to be the very commercially, many companies are attempting, and many people have conceived and floated and invested huge money onto that, and our industries can also look into it. Coming to the RLV technologies, this is an upper stage recovery. We need to go for the full recovery phase. So we have already demonstrated the HEX mission, that is a hypersonic experimental mission, and RLV mission, the landing experiment. Both phases are now demonstrated. Here it will go for a full entry and orbital entry and the re-entry mission, and then it would come and land on a runway just like any other aircraft. And few of the figures of the critical technologies are listed here, which we need to master before we fully declare it operational. And coming to the air breathing project or air breathing applications, we know that the ISP of the air breathing engines are very high. And there are multiple domains are there. There is ramjet is there, scramjet is there. And already we have done 2 experiments. One experiment was conducted in 2016. And recently in 22nd July 24, we conducted the second experiment. And the hypersonic vehicle can go to an appropriate altitude, pick it up, and this mission or this program is also a declared program of ISRO, where we will have a sustained acceleration for nearly 250 seconds of 0.2 G. And this demonstration will be done in the coming years. And this will lead to increased specific impulse, will lead to quantum leap in the vehicle performance. And electric propulsion, this is again a summary of advantages I have listed here. And we are also working at an initial level of 18 millinewton and the 300 millinewton. This will be demonstrated in a short time. Already 18 millinewton is already flown. And the different types are available, and they have a specific applications and then appropriate orbit and the end use. We can choose and then go for it. We can see that the ISP is very large as compared to the conventional rocket propulsion system. And many of the orbits or many of the experiments, we will not be able to carry a conventional rocket propulsion there. Coming to the planetary exploration, already as we all know, we have already done the Aditya L1, Chandrayaan 3, the Mars orbiter mission. Chandrayaan 4 is already slated for 2028, and which will have a sample return mission. And the Venus orbiter mission also is now declared by the government. We will be going for that. And it is all for the planetary exploration and understanding the science mission. This is a view graph I took from the NASA, where you can see that one is an Earth dependent and another is an Earth independent. There are planetary missions where we need to go and do the studies. We need to go beyond and we cannot depend on Earth, and those are called the Earth independent. But from going from experiments from Earth dependent to Earth independent, we need to do a lot of proving grounds. And they are the one we talk about in using the moon. So moon will be an intermediate point for all technology demonstration and moving forward. So what it means, and also we have a very interesting and curious missions that have been undertaken by others. where they have collected the sample from asteroids, because asteroids are remnants of the building blocks that formed the planets and maybe still having an embedded life in that. So there are samples that have been collected from the asteroids by the other organizations. And if we intend to do, we are capable of doing it by using these vehicles available with us. Now, but a typical mission duration you can see. So you will have to wait. If you are, it's not that today you launch and tomorrow you are going to get that. But they are all long duration missions, but they are all feasible. It can be planned and executed within the capability of ISRO. Coming to the lunar exploration, only Chandrayaan 4 as of now, we declared that we will go and return the sample. But when you now look into the long-term utilization of Moon as a launching ground for further deep space applications, we need to do a host of activities, and there has to be a lot of robotic landings and then experiments conducted there. And then we need to have an Artemis program kind of a habitat at the lunar orbit, which is already declared by different countries. Even China has declared, Russia has declared, US has declared Artemis program. So there are going to be a habitat or a module sitting in the orbit of lunar Moon, and vehicles will go and then land, and from there an ascent and descent vehicle will be there. Because every time carrying an ascent and descent vehicle along with its propulsion from the ground will be impractical, or it will not be economically viable. Hence, we have a system. We need to plan so much of activities or something if you want to have a permanent base at the surface of the Moon. Chandrayaan 3 has, you know, that this was our flagship program. Last year we launched and then landed on August, and which we celebrate as a National Space Day. 1 year time was recently we crossed the National Space Day. We had happily celebrated. But then how to go about the Moon? There are different, when we now try to talk about the sample return missions, they are typically few 100 kgs or less than 10 kgs kind of a sample only we do. Now, if you want to carry huge masses or the payloads to that, we need still heavier vehicle, bigger than the NGLV. So whatever the studies or efforts we make it, the vehicle configuration should be again a modular, and we should be able to plan for the future also. So we need still heavier launch vehicle. There are different methods of reaching the lunar surface is possible, and the appropriate decisions have to be taken. And the key technologies that are to be developed to have such a Moon missions are listed here. Most important is the long duration sustenance of the crew. Then we need a very heavy launch vehicle capabilities, that is 150 ton. Today we talk about 30 ton by the NGLV. Whether 150 ton class of vehicle is required or multiple modules I can make and then dock in orbit and further proceed. These are all the options we need to study in space propulsion, because we need to have a sustained life on the surface of the Moon. We need to have an in situ resource utilization, deep space navigation and communication. All these abilities we need to build. And these are embedded as part of the program what we have now declared. So when we try to consolidate the activities, I feel these are the areas that are going to really play a role. One is the propulsion system. We need to have a new propulsion system, which is already, we have commenced the LOX methane 1100 kilonewton engine we have already done, but we need to go for either a more optimized cycle or even a still heavier thrust engines are required when we now undertake such kind of a very heavy missions. Then materials and manufacturing are going to change the game altogether, because the way we manufacture makes all the difference. And the materials what we have been using in the 2020s or 2010 has to be now improved upon by different processes and the manufacturing methodologies, and have to be very optimally utilized. So, there is going to be a very lot of changes. There are plenty of alloy steels or alloy materials we are developing. And thermal control systems, it is not only for the sustained human presence in the space. To come back, you'll be encountering very enormous amount of heat fluxes, and we need to survive and then bring the humans safely back to the Earth. And for which we need to develop a host of thermal control systems. Coming to the avionics and the robotics, AI and sensor, this is again a huge potential that is in front of us in terms of communications, deep space communications I talked about, and carrying out experiments every time human cannot go there. And these areas, there are plenty of scope. Then activities have to be thought about and then implemented. And coming to the energy systems, again, it is a very, very important area. We cannot go using a conventional methodology of energy. We need a very high, what you say, energy density, we call it. It is the energy per unit mass, the weight of the system. We need to have a new systems. There are plenty of research happening world over, and we also need to be at the cutting edge level in order to compete with them. And the space reforms, this is only one slide I have put in. You can see that today only 2% of the world space economy is being operated by ISRO, $8 billion. And then the policy, government has now declared a policy that we should ramp it up to at least 8% by 2033. And then by 2047, we should observe at least 15%, because whatever the knowledge we have gained by doing governmental missions, we have achieved the self-reliance in terms of design and development for the applications what we require for human or Earth observations. Now, that has to be commercially exploited, or that has to be commercially converted, so that the entire India gets benefit out of it. So the industries have to be now ramped up to enable the space industries to go from today. We give the build to print, that is, we give the specifications to them. But then by hand-holding on many of these projects, what is declared at the bottom, we are trying to hand-hold the industries. They will be included right from the beginning part of it, so that they will be enabled to build it to specifications, so that they will be the joint development can be there. And there are plenty of startups are coming up, and it is open for them to pick it up any of these areas and come out and contribute. So this will accelerate. Now we can see that many of the projects are declared. This runs into something like 30,000 crores, which is a very huge money. This goes expenditure primarily to industries only back, because hardly 10% only is the foreign content, and balance is totally going back to the Indian industries. And the benefits are industry growth. There is going to be a socio-economic benefits out of that. MSMEs, SMEs, all will get benefited, and they all will get international recognition, and they can become at par, and they can take up job from other countries also as a viable player, enable the industries and the NCL and in space of enabling them. So this is a summary slide. I am just making it. We started from a very humble beginnings of 1960s. That is, we hardly had a 30 kg into 100 kilometer orbit. That was our capability in 1963. From there, we have grown to put some kind of a 10 tons to 400 kilometers circular orbit by Mark 3. And then we are trying to aim to put almost like 30 tons into 400 kilometers circular orbit by 2031. And it is all is possible. All the missions all are demonstrated our understanding. So we need to only put forward all our best foot forward and work towards it. Thank you.